A very pleasant day to everyone. It is indeed an honor to be addressing such an esteemed crowd. My name is Maegala Nallapan Maniyam and I am currently attached with University Selangor, Malaysia. Without further ado, I would like to proceed with my presentation entitled Conversion of Waste Cooking Oil by Rhodococcal Lipase Immobilized in Gellan Gum. I will break my presentation into 4 different components, namely the introduction and research objectives section, followed by the methodology adopted to carry out the study, the explanation for findings, and finally the conclusion and recommendation for future studies. Let me begin this presentation by saying that Malaysians love fried food. This is reflected in the numerous stalls and restaurants selling fried chicken, fried bananas, and French fries in Malaysia. In fact, a study conducted by Chi et al. In 2017 found that almost 18 participants out of 35 respondents in a survey consumed fried food 3 to 5 times per week, which indicates the popularity of fried food in Malaysia. Hence, large amount of cooking oil is required in the food preparation, which simultaneously yields a similar portion of utilized cooking oil or waste cooking oil. Therefore, the mass presence of waste cooking oil in Malaysia should be exploited for beneficial applications. However, we can actually see a few research gaps in using waste cooking oil. Firstly, in Malaysia, the requirement of biodiesel is not very crucial because we are petrol exporting country and our hybrid vehicles are still very limited. Secondly, waste cooking oil conversion involves the presence of chemical catalyst, which is not very environmentally friendly. And finally, another byproduct of waste cooking oil conversion, which is glycerol, can be used in the food industry. However, the enzyme commonly used for the conversion originates from porcine. This is quite a challenge since majority of Malaysians are Muslims. So to address these challenges, we proposed the utilization of green biocatalysts known as lipase from bacterial strain for the conversion of waste cooking oil to glycerol. Therefore, the objectives of the present study are to determine the most optimal metrics for lipase immobilization for enhanced conversion of waste cooking oil and to evaluate the repeated use of the immobilized lipase for waste cooking oil conversion. An amount of 100 ml of minimal salt medium was used as the production medium, which was inoculated with 12% of pre-prepared inoculum and incubated overnight at 30 degrees Celsius and 160 rpm in an incubator shaker. The mixture was then centrifuged to separate the cell mass. The enzyme was then extracted from the cell mass using cryogenic method. The protein concentration and lipase activity were determined using UV spectrophotometer respectively. 5 mg of crude lipase was then immobilized in calcium alginate and gellan gum, resulting in the formation of 50 beads respectively. These pictures show the immobilized lipase from Rhodococcus predinivorans strain UCC0009 in calcium alginate and how the separation was carried out to obtain biodiesel and glycerol. Table 1 shows that the lowest conversion of waste cooking oil was observed with free crude lipase extracted from Rhodococcus strain UCC0009, yielding 38% conversion. Fascinatingly, substantially greater waste cooking oil conversion was observed with immobilized crude lipase in both matrices compared to that of the non-immobilized counterpart. The improved waste cooking oil conversion may be attributed to enhanced rigidity of the enzyme, which shielded it from unfolding and avoided the conformational transition of the enzyme. The employment of the crude lipase extracted from rhodococcal strain UCC0009 and immobilized in gellan gum surfaced as the most proficient method in the conversion of waste cooking oil, yielding 83% conversion, a considerable increase in the extent of waste cooking oil conversion by 36% and 180% compared to the use of calcium alginate immobilized crude lipase and free crude lipase in waste cooking oil conversion respectively. The employment of gellan gum bits for effective waste cooking oil conversion was found to be favorable since the method provides chemical, mechanical, and thermal stability. The reusability performance of the crude lipase extracted from rhodococcal strain UCC0009 and immobilized in gellan gum, which was assessed for 9 consecutive cycles for waste cooking oil conversion, is as shown in Figure 1. The gellan gum immobilized crude lipase maintained its activity for 7 successive cycles, resulting in an average of 85% waste cooking oil conversion. It was interesting to observe that very minimal amount of cell leakage occurred at cycles 8 and 9, which may be due to the washing process at the end of each batch. The findings from the present study indicated that the crude lipase extracted from rhodococcal strain UCC0009 and immobilized in gellan gum exhibited good reusability as biocatalysts. In conclusion, the utilization of gellan gum immobilized crude lipase resulted in improved lipase activity by 118%. In addition, the collective findings from this study simultaneously provided solutions for waste management, whereby we are converting waste cooking oil into useful products, and also promoted the use of green biocatalysts for industrial applications. These are some of the references that I have used while conducting this research. Finally, I would like to acknowledge the Selangor State Government and University Selangor for providing the grant to carry out this research. I would like to end this presentation by quoting a brilliant person. Recycling turns things into other things, which is like magic. Thank you.